So in the last videos, we learned what it means to be a morphism between locally ringed spaces. And with this done, we now also know what it means to be a morphism between affine schemes, because those are locally ringed spaces. And so the morphisms between them are just the morphisms of these underlying locally ringed spaces. And with this, we can make precise a correspondence which gives us basically a bijection between rings and affine schemes and makes this precise on the level of categories. And to get started, recall that we have already seen something like this in a kind of more special case. Namely, we have seen that affine varieties over an algebraically closed field K are in one-to-one correspondence with finitely generated and reduced K algebras. And the correspondence just send the variety to its coordinate ring. And now we can finally generalize this to like a category here, which is more natural, namely just a category of all rings. And the heart of this result is the following proposition, which says that for any two rings R and S, we have a bijection between the morphisms from spec R to spec S and the ring homomorphisms on the commutative algebra side from S to R. Notice somehow the order here is reversed, right? So somehow the ring homomorphism goes from S to R, and the morphism on the geometric side goes in the opposite direction from spec R to spec S. But this was already the case in the affine variety situation. And this one-to-one correspondence is kind of easy to write down in one direction, because if you start with F, then you just send it to this pullback ring homomorphism, F star, which is the global one, so on sections on the entire spectrum. We're going to recall this in a second. So there's this one-to-one correspondence. In particular, we have a natural bijection going from affine schemes modulo isomorphisms to rings modulo isomorphisms, and this is just because somehow if you have two affine schemes and you had an isomorphism between them, then via this map it would go to an isomorphism between the two rings and vice versa. And so this is the heart of the matter, this proposition. And now we're just going to go through this and show this. And the first part of the proof is to argue that this is a well-defined map. And just also to recall what this means here. So let's say we have F going from spec R to spec S, then by definition of a morphism of local ringed spaces, this is not just a continuous map, but then we also have these pullback maps on all open subsets of the target. So in particular, on the open subset of the target, which is the full spec S, it will give us a ring homomorphism. So it starts in O spec S of spec S. The functions on the full set going to O of spec R of the preimage, but the preimage of everything is everything. So this is spec R. And then we have already seen that the global sections, so the global regular functions, this is just S, and this is just R. And so indeed, this map is well defined. We do get a ring hom at this point. Okay. So we're off to a good start. At least we have a well-defined map. And what we're just going to do to prove that it's an isomorphism is we're going to construct the inverse map. And so we start off with such a ring homomorphism phi from S to R, and then we need to construct the data of this morphism here. And that's also a good exercise, because then we recall what is all this data that we need to provide if we want to specify a map between affine schemes. Okay. And so we're going to construct this f, which should be the image. So somehow if the inverse map is big psi, so we want to define what does psi of this ring homomorphism f phi mean. So we want to go from spec R to spec S. And well, the first, so somehow to specify this thing, recall what we want to do is we want to specify a map of underlying sets. It should be continuous. This is the first part of the data. And then we need to specify what the pullback does on all open sets. So for the map of sets, here, as you can see in blue, we have the first little lemma, which is somehow crucial, which says that if you have such a ring homomorphism and you have a prime ideal in R, then its pre-image under the ring homomorphism is a prime ideal in S. Just follows from the properties of the prime ideal. And with this, we have a good idea that if we start with P inside spec R, it will just be sent to phi inverse of P, and this will be a prime ideal in S. So the lemma tells us this is well defined. And the next thing we need to do is we need to check that it's continuous. And so for this, we just check that the preimage of a closed thing is a closed set. And so, well, what are the closed sets in spec S? Well, they're just cut out by ideals. So let's say J inside S is an ideal. And V of J is the set of Q and S prime, which contain J. Right? And so then we compute the preimage. So it's all the P inside R prime, such that, well, we want that J is a subset of Q, which is phi inverse of P. Like this. But then this containment here, J, is a subset of phi inverse of P. This is equivalent to just saying, well, if you apply phi on both sides, you get that phi of J is a subset of P. But now we have transformed this. This is the prime ideal of P containing phi of J. And this is just by definition the vanishing locus of phi of J. And so somehow the preimage of this closed thing is a vanishing locus, and so this is closed in spec R. So basically, I mean, that's the nice thing about schemes. So somehow all of this basic topological stuff is very easy. It's basically just playing around with set theoretic inclusions. Okay. And the next thing that we need to do, and that's already kind of the final thing to construct the inverse map, is we need to say that given V inside spec S open, I need to define the second part of the data of a map of locally ringed spaces, namely this FV star, going from O of spec S V to O of spec R of F inverse of V. Okay. And just to recall, what are those things? How did we define these sets of regular functions? Well, this here will be a collection, sigma Q. All of these will be in the localization of S at Q, when Q is in this open set V. and they should be locally given as g divided by f. And similarly, these things will be eta p in Rp or p in f inverse of v, which are locally given by some g tilde divided by f tilde. So this we need to do. And here, kind of on the next page, let's just summarize. I just copy pasted this again so that we have it here. So in other words, given such an element in here, so we have these sigma q's and these sq's for q and v, we need to specify this collection here. So in other words, for each p in this pre-image, we need to specify what is this this fv. I guess this should also be fe star here. So somehow, what should this thing here be? And so somehow for each prime ideal, we need to give an element of this localization. And again, we use a result from commutative algebra, which says if you have such a ring homomorphism and we have P in R, a prime ideal, then we do get a map between the corresponding localizations. So somehow we have this RP here, and we have we know that phi inverse of P is a prime ideal in S. So we also have this localization. So these are two local rings now. And well, what can we possibly do? Well, we have this quotient of two elements in S, and we have a ring homomorphism here. So the only thing we can think of is we can just apply the ring homomorphism in numerator and denominator. And what the lemma then says is that this is a well-defined ring homomorphism. In particular, note somehow some basic well-definedness check is that since f by assumption is in the complement of this prime ideal, so f is not in phi inverse of p, then if you apply phi, then phi of f is also not in p. So somehow this allowed denominator here goes to this allowed denominator. That's already good. So this is a well-defined ring homomorphism, and it is even a kind of a homomorphism of local rings in the sense that the preimage of the maximal ideal in the target is the maximal ideal in the domain. And so this puts us in a pretty good spot, because now we can just write down what the image here should be. We have this collection of things, and this sigma q, this is exactly in here, in one of these things. And so we now need to specify what eta p is, where p is in f inverse of v. But then what we just do is we apply this phi p from above to this sigma of phi inverse of p. And note somehow this condition that p is in the preimage here means that phi inverse of p, that's f of p, that this is indeed in v. And so we have access to this information here. We can apply this and we get this element. And it's exactly where we want it to be. And so this is already the full thing. We just apply this map on the stalks essentially. And then we make a couple of checks. So first of all, remember that we didn't just have arbitrary collections of these elements of the stalks, but we want them to be locally of the form being a quotient. And so we need to check that this property is preserved, but so somehow if the sigma q is equal to g divided by f locally, then this eta p is equal to, well, exactly apply phi to numerator and denominator. And so this is given by this here locally. And so it's a well-defined map. And And then also because phi is a ring homomorphism, it's also true that this thing here, that this thing is a ring homomorphism. And it's also compatible with restrictions. This was the first property that this collection of pullbacks should satisfy, that if you first restrict, then apply it, it's the same thing as first applying it and then restricting. But since we basically just do something pointwise, it's clear that it doesn't really matter whether we first restrict and then apply it or vice versa. So that's okay. And then now if we look at what does this map here do on the stalks, then, well, we have defined it basically by saying what it should do on the stalks. So it should be exactly this map phi p on the stalks. And then essentially the second lemma here tells us that this thing is a map of local rings, by which I just mean it pulls back the maximal ideal to the maximal ideal. Okay. And so we have verified all the properties. And so somehow that's this F, and then this FV star is an open subset spec S. That this going from spec R to spec S is a map of locally ringed spaces. And then the final thing, so we have, let's go back where we are at the moment. So we have seen this thing here is a well-defined map, and now we have constructed a well-defined inverse. And then what we need to do is we need to check that this well-defined map in the other direction is an inverse. In other words, we would have to check that both compositions are given by the identity. And so, so for example, if you start with a ring homomorphism, and then you go through all of the steps that we had here. So you start with the phi, you construct this F, and then you look at what does F star do on the global sections. Then you want to get back phi. But this is somehow, this direction is pretty easy to verify, because somehow where we do get, if we apply this thing in the other direction, we get another ring homomorphism. And by definition, like how we constructed these things here, it's a ring homomorphism which does exactly the same things on the local rings, on all of the local rings. And this then implies that that you indeed get exactly back the original thing. And the other direction is then we'll just leave it as an exercise. So somehow check that the big phi, the big psi are inverse maps. So I think the most important thing is to understand what they do, and then this final check is more like a bureaucratic verification. Okay, so this was the proof, and so we see that if we express this in fancy category language, then we can now say that there's two categories, namely affine schemes and rings, and there's a contravariant functor between them, which takes an affine scheme and sends it to its ring of functions, and it takes such a morphism here and sends it to this pullback. And that this functor here is an equivalence of categories. And basically what we checked here is that on the level of morphisms, this is a bijection. Note the map in the opposite direction. We have also kind of seen, namely that if you have a ring, then you get the affine scheme associated by taking the spectrum. So this is the inverse functor. And then what we basically did in this proof is take a ring homomorphism and then applying kind of the spectrum, we got a morphism between the two spectra, or to the two affine schemes associated to it. So this shows that somehow this full theory of rings is, by some abstract nonsense, equivalent to the full theory of the affine schemes. And this is the geometric realization of everything that you learned in commutative algebra now has these kind of geometric objects associated to it. And this result here shows that essentially anything which must be possible for rings, there must be a similar construction on the geometric side to do it. Okay, so this is everything in this video.